Alright, it's Tuesday, you're at school, and I'm in Jamaica Mountain. I'll try not to rub that in. Oh wait, I already am. No woman, no pride. Alright, I guess I've made y'all jealous enough. We can actually do a little bit of math. Maybe. Okay. Let's see if I know what I'm doing here. Alright guys, today we're going to keep talking integration, of course, and today we're going to go and transition from the indefinite integrals from yesterday into what's called a definite integral. So the way that this is going to work is it's going to continue from yesterday, but bring back a little bit about last week. Last week, you remember we talked a little bit about area. Well, I'm about to make a very profound statement here. Okay, there are times when you are taking the integral that the integral or the antiderivative of f of x is actually equal to the area under the curve. Yes, that's right, folks. Definite integrals are equivalent to area under the curve. Alright, some of you are saying what, and some of you are saying I don't believe you. So I'm going to try to make you a believer. It's pretty freaking cool to me that when we take a derivative, we are getting the slope of a curve. And when we're taking an antiderivative, we're getting an area under the curve. That's a little mind-blowing. So I want to try to help put it in perspective, and I want you to look back at something from last week. Whenever we first did area approximations, I believe we were working with the square root of x, and we had really focused from when x equals 0 to x equals 4. And we had done all of our little different approximation methods. You got all these little different areas that you got. And so the statement that I'm making now is that we could have avoided all those approximation techniques if we had just known how to take an antiderivative or an integral. And so what I'm going to do is I'm going to integrate the square root of x under this curve, and we'll get a formula. I mean, this was all day yesterday. So take a second and integrate that, and let's make sure we get the same thing. I guess you would first rewrite that as x to the 1/2, and then our rule says that we need to add 1 to this exponent, which means it's now x to the 3/2, and then this is all over 3/2. Now the same thing as being all over 3/2 is really just 2/3 times that x value. So this right here, not surprising. And of course, yesterday we learned that we would like to have that plus c. But I want to relate this. This is still an indefinite integral. I want to relate this to area and then turn it into a definite integral. Okay. So if we are studying the curve square root of x from 0 to 4, what I'm telling you is there's a way to take this equation and approximate area. Well, if we want to approximate the area from 0 to 4, then guess what? Take that 4, plug it in there, and see what happens. Okay, 2/3 times 4 to the 3/2. Okay, now I'm going to lose my plus c for the sake of doing area, and then once we write a little definition or theorem here in just a second, it'll make sense why the plus c is not needed. But right now, plug in that 4, and let's get a number. I guess it's going to be, I'm going to do the square root of 4 first. So square root of 4 is 2. 2 cubed is 8. And then we're going to be doing 2/3 times 8, which is 16/3, okay? Now, look back, if you haven't already flipped back to what we did last week, look back and look at all the different approximations that we had written down for the square root of x. We did a right-hand limit, we did a left-hand limit, a midpoint limit, and probably trapezoidal limit. If you look at those 4 approximations, I'm guessing some of them are pretty darn close to that. And with calculus, we are saying that that is the actual area under the curve. Mind-blowing, isn't it? I think it's amazing. I think it's pretty impressive to think that the derivative will give us the slope of the curve, but the antiderivative will give us the area under the curve. Pretty stinking cool. Okay, so before we go on, let's talk a little about notation, and let's talk a little bit more about this area and why it has to be positive, okay? So first of all, for a definite integral, what you're going to be doing is you're going to be putting bounds on your function, okay? You're going to be saying there's a beginning point, in this case it was 0, and then there's an end point, which in this case was 4, where we are concentrating our focus for the antiderivative. So the way that you're going to write it is you're still going to do like indefinite integral, like this, okay? But you're going to put bounds on your integrand symbol, okay? So for this one, I'm going to go 0 to 4, because that's what my picture's saying. And so for this problem up here, I could have done 0 to 4. And, you know, it's not always going to be 0 and 4. So if we want to write arbitrary variables, why don't we just erase that? All right. Oh, that's a huge eraser. Huge eraser. Okay. Let me do A and B. How about that? Okay, cool. This right here is the notation for a definite integral, and this is telling you to integrate your function, but from A to B, meaning your lower bound and your upper bound. Okay, that's what those represent, lower bound, upper bound. And what you have to do to evaluate the function is once you take the integral, you plug in the values, okay, kind of like I did just now with this 4. So we take the integral, capital F for integral, of f, okay, of that f of x function, but instead of just having an x here, I'm going to plug in my b value. Now, on the one above, my a value was just a 0. That's not always the case, so we have to somehow account for that 0, or if that's not a 0. So you're supposed to plug in your upper bound and take the integral, and then do the same thing. Take the integral, plug in your lower bound, and you're subtracting those two values from one another. I think that's going to probably make sense in your mind if you think about the fact that the 4 is the upper bound, the 0 is the lower bound, and you're trying to contain yourself in that area. So subtraction is a great way to talk about distance between things, and that's kind of why that falls into place, okay? So this right here is a good flashcard, I think. Ooh, all right. And what we're going to be doing is figuring out when we use this for area and then when we just use this in general, okay? Now, the key here is you can use this anytime. If I give you a definite integral of anything, you can always do the math and plug in the numbers and get an answer as long as your function is continuous. If you want it to represent area, though, guys, we do need to make sure that the curve, if the curve is continuous, applicable is a good word here. Wait, if I can spell it, applicable. Ooh. Area is only applicable if f is continuous and non-negative. Don't you love the word non-negative when they could just say positive? We're going to go with non-negative though, just to really, really make it important. Okay, you can refer to it as area only if it's continuous and non-negative, okay? Otherwise, you're just finding a number. So I'll kind of do a couple examples to show you the difference, okay? So let's go ahead and look at, let's see if I can scroll here. Let's go to the next page. Let's do another example of a definite integral and then what it's going to mean. So let's do the following, x plus 2. And let me restrict us between 0 and 3. Okay. Take a minute and integrate that, and then we'll plug in our values together, okay? And I'll also show you some notation along the way. So you take a second and split those up and integrate. So I guess you're getting x squared over 2, or hopefully you're getting x squared over 2 for this one, plus 2x for the other one. Now you can either write them separately as I did here, and then we'd have to plug in our bounds separately, or if you don't want to think about it as distributing the integral, then just take the integral of each piece, and then we're applying our 0, 3. And the notation that you see a lot of times is a straight line behind the function, and below that the 0, and above that the 3. So when you see me draw a straight line, or really anyone in the math world, what we're saying is I've already taken the integral. Now I'm going to plug my stuff in, okay? And so that's what I'm going to do. I'm just going to write that. Straight line says, hey, here, I still have bounds that I need to pay attention to, but now we're going to plug in. So if we plug in the 3, we get 9/2 plus 2x. Sorry, it's an x there. 9/2 plus 2x, which means 2 times 3, okay? And then minus, now I'm going to plug in my 0. Which that's all going to go away, which is all good and fine. But let's get the number that comes from this. We've got 9/2 plus 6, which is 12/2. So that means we're staring at what, 21/2? Woo! All right, 21/2. So with relationship to this problem, you know, hey, 21/2 is the definite integral, but we can call that area. And the reason we can call that area under the curve is because if I sketch x plus 2, well, let's change colors here. If I sketch this out, it looks a little something like that. A little something like that. But we're cutting ourselves off from 0 to 3. And so if we're doing that, we're focused on this, and this meets the two criteria, which says that we are in an area that is non-negative, so all of that's above the x-axis, and it's also a continuous function, okay? I understand that this function goes below the x-axis, but not in the part where we were asked to look, so we don't have to worry about that. We were only asked to look between 0 and 3, so isn't that awesome? So that's the area right there, and if you did a trapezoid, a formula of a trapezoid right here, and you knew that height, and you knew that height, and you knew that base to be a 3, guess what? You're going to get the same area as 21/2, which is what the calculus just showed us. So math's pretty awesome sometimes. All right, for a second example, I want you to look at this one, and let's decide before we even start if our answer is going to represent area or not. So think about it. What does that look like? Where are those bounds? Okay, that's enough time. Hopefully you have thought about the picture and decided it's, 2x is a little steeper, so it looks something like this. We're restricting ourselves from -2 to 1. So if you go to where that hits the curve and where that hits the curve, this is negative, okay? So in terms of area, when we get an answer, it's kind of hard to say that the area is equal to something because we're looking at these two weird pieces, and your question might be, well, is it going to give me the area of that and the area of that? Like what's happening here? Let's go ahead and do the problem and look at our answer and then try to reason through it. The integral of 2x is just x squared. Well, and that's it, just x squared. So it's just this parabola, and we're going from -2 to 1. So what we're supposed to do is plug in the 1 and square it, and then minus, plug in the -2 and square it, okay? And what do we get here? We get 1 minus 4, which is -3. So that answer right there should just tell you that this is not area, because, my God, we got a negative quantity. And how can area be negative? But for those of you that want to still see how it ties into area, think of it this way. -3 is the answer for the whole problem, but that can actually be found from studying the area under here along with the area here. And what happens is, since this is under the curve, you find the area, which if you just did this part from -2 to 0, I believe that area would be 4. But since you're under the curve, you call it negative. And the area of this little piece right here, this baby piece, would be a 1. And so the net between the -4 and the +1 would be a -3. So it's not good to say the area is -3, but just so you know what you're looking at, that's kind of what it means is, under the curve area you could call negative, over the curve you could call positive. So whatever floats your boat there, people. Okay, what I'd like for y'all to do is check out there's some cool definitions and properties in the book on page 276 and 277. I think there's 3 boxes total. This is the only extra reading outside of this video that you need to do today. And then I'm going to have you try some problems on page 278 and 279. We're going to go with 13 to 45 and then number 47. These are some great problems, of course, all odd. I'm not that horrible. All odd. I know it's a lot of practice problems, but it's the same bloody thing as yesterday, except now you have upper and lower bounds. So just make sure that you're following that nice formula, the one that we just saw that, where is it? Oh, that's not it. That one right there. Make sure you're just plugging in. Take the integral, plug in the b, minus the integral, plugged in the a, and you're going to get your nice little formula. So good luck and have fun with that.